Continuing our discussion of chemical reactions, we want to talk about reactivity patterns. We're comfortable using chemical equations to represent reactions, and then we want to spend a little bit of time parsing out or analyzing those chemical equations. And what we can do is we can analyze them based off what are called reactivity patterns. We have a lab about this called types. They're also called types of reactions. That's what the lab is about. There's also, and the book talks about that. And so what we want to do is basically just take overall reactions that are involving different types of chemicals and recognize different types of chemical changes that we can really see. So we have 4 types, and we'll just want to introduce them here, and then we'll talk about them in detail. We have combination, which is multiple reactants becoming one product compound. The operative word there is one product. We have decomposition, where you have one reactant, so the opposite of combination, becoming many products. You have single replacement, where one atom type switches between the reactants. You'll note it is one atom type is what we want to focus on. That's where the word single comes from. And the switches is then replacement. We then have double replacement, where all atoms swap partners. Generally, when we're doing reactions, there's 2 compounds. So that's where the double comes from, all atoms. And again, replacement is the swapping partners. So you change that idea of replacement, you are changing where the bonds are. So combination and decomposition are pretty big time changes. You go from elements or from multiple, from more than one compound or substance into one or vice versa. And then in replacement, you can see that there's kind of just a smaller change that's going on. So for our combination reactions, we know the key feature that we're looking for is one product. Combination reactions feature one product and more than one reactant. It can be 2, 3, 4, whatever it is. You can have elements combining to form a single product. An example of that would be burning. This is burning magnesium. You'll see that in the lab, where you are, kind of lighting it up in oxygen to make magnesium oxide. You can also do have combination reactions that involve compounds. So calcium oxide plus water gives you calcium hydroxide. So anything like that, as long as you make one product. In combination reactions, you can use this theoretically to make any compound, right? Any compound can be made up from combining smaller substances. One of the things about these is you'll note from that photo that is quite a bright light that's being produced. There's a lot of energy generally associated with combination reactions. And so that can be potentially a little harder to control. That's dangerous to look at. The camera's protecting your eyes from UV light burning them. And so that's something we generally, we don't necessarily use combination reactions functionally because of how energetic it is to make compounds out of elements or out of smaller compounds. Decomposition reactions are then when we create multiple products from one reactant. And generally, when we think of chemical reactions, we usually think about trying to create a product, right? We do chemistry in order to make interesting compounds or whatever we want. And so decomposition, generally we don't think of as necessarily a useful product or useful process, but there are plenty of instances industrially where we want to use it. So for example, NaN3 is called sodium azide. And so when you take this sodium azide, if you take this solid and you hit it hard enough, it will undergo a reaction where you make solid and gas. This is the reaction that underlies airbags. So this is a solid that's sitting inside your steering wheel or on the passenger side of the vehicle. It gets hit with like a piston when that's activated by your car crash. And then all of a sudden you make gas. And importantly, gases really expand. And so that's how you fill this airbag really quickly with a lot of gas without having to carry around a gas tank. And so that's really going to help you fill it up. It's also important to know that the gas you make in this process is nitrogen, which is an unreactive gas. It's what most of the air is. So that's why the airbag isn't dangerous. You wouldn't want to fill it with like a toxic gas or potentially hazardous gas. And so this is a chemical reaction that people have been able to figure out that's decomposition that we can use usefully. in this sort of safety measure. You're not making necessarily anything you want to use, N2 isn't that useful in terms of a product, but it is potentially saving your life. Your body also performs decomposition reactions. You eat complicated molecules in your food, and you break those complicated molecules down into something more manageable or much more useful, and your body takes those kind of building blocks and combines them into the molecules that you are made out of that are much more complex, using combinations in there. So you break down in decomposition, and then you combine into bigger things that your body is made out of. So single replacement reactions then. Replacement reactions are something that we see, these are a lot more functional, or that we would use in a chemistry lab setting. So in replacement, that word is all about basically swapping atoms. What that means is you'll note this kind of stereotypical pattern. In single replacement, especially when we're dealing with one atom, you react an element with a, well, let's get a better color, with a compound, and you make a compound and an element. Get that colored correctly. Compound and an element. So you'll note that there's there's always a reactant and a product that are both elements. That is a sign of a single replacement reaction, where you're seeing that change. Basically, zinc in the reactants, Zn, is in its elemental form, and copper is in the compound, and they swap places when you go into the product, where now copper is the element and zinc is the product. These are much smaller changes usually. So this is a picture of this example, this reaction being performed. Here is the zinc. It then basically goes into the aqueous phase, and then copper, which was dissolved, this blue color was due to dissolved copper. Now that copper is attached to the metal as little bits, and there's some that have fallen down to the bottom right here. And you can note that the color of the liquid is now less blue. That's because you've made zinc ions, which are not colored. Zinc sulfate is colorless. And so you have this nice transition, and it's small and controlled. You see there's no smoke, there's no heat, there's no bright light being performed. This is a much subtler and easier to control reaction. So functionally, we use replacement reactions in the chemistry lab. Double replacement then offers similarly controlled reactions, but you get more changes happening at a time. It's same replacement in that you have a lot of changes, but you're swapping multiple atoms at a time. You can characterize double replacement because you can see compound plus compound makes compound plus compound. So lots of changes, but you have multiple products. There's no elements involved. Everything is in a compound, reactants and products. And so ammonia plus your sodium hypochlorite, you get sodium hydroxide and this NH2Cl compound. So this would be an example of a chemical reaction that really quickly happens. It's very easy to make occur, but you really don't want to. It's not necessarily dangerous on face. There is some heat involved, but it's not too bad. This is just an example of a chemical reaction we want to be aware of because ammonia NH3 is the active ingredient in Windex, NaClO. Sodium hypochlorite is the active ingredient in bleach. And so these are both cleaning supplies. Sometimes people think, man, I'm going to make a super cleaner by mixing these things. The problem is you make NH2Cl gas, which is toxic. And so what would happen if you mix these substances together is that you make a toxic gas. And oftentimes we do this in, say, a bathroom. Now your bathroom is full of toxic gas, which escapes the liquid, goes into your lungs, and can cause you to pass out and die. So this is an example of being aware of a chemical reaction that can happen that we should want to avoid. And so, we were looking at these ideas, chemical reactions. A lot of times we don't necessarily want to know them just because we can do them, but a lot of times to be aware of when we don't want them to happen. Okay, only one more video left in the set. We're looking for any more questions on participation 611. I'll see you in that final video.